Hi, I am Rajat Gangrade. I'm a PhD candidate in underground construction and tunneling, working under the supervision of Dr. Mike Mooney and Dr. Whitney Trainer Guitar. The topic of my presentation is a probabilistic assessment of karstic void risk in tunnel projects. First, let us talk about tunnel boring machines, TBMs, the machines that take a bite of the ground to make tunnels. These machines have been successfully used in congested urban settings such as Mumbai, New York, Chicago, and Sydney. The machines not only excavate the ground but also install concrete segmental linings or concrete rings to support the tunnels. As you can guess, the knowledge of the ground is very important for the operation of these machines and a safe and efficient construction of the tunnels. And these machines are very much a state-of-the-art practice. For any tunnel project, the largest technical and financial risk lies in the ground, predominantly due to the specific ground features that affect tunneling. One such ground feature affecting tunneling are the solution cavities and voids formed due to the dissolution of carbonate rocks such as limestone or gypsum in karstic geological settings. A significant construction issue with karstic voids is water ingress, causing disturbance to surface structures. In this video, we can see the consequences of water ingress into a tunnel causing damage to the surface structures. Multiple case studies from Malaysia and China indicate that unpreparedness in estimating karstic void locations can result into hazards. For tunnel projects planned in geological environments, the detection of voids in the driving path of the tunnel boring machine has always been a critical issue. You can see on the figure the irregularities in the rock head elevation of limestone in this case can cause severe damage to tunneling operations. The current practice lacks a quantitative assessment of karstic void occurrence, such as what are the number of voids, size of the voids, occurrence probabilities, frequency of voids in the tunnel envelope are not answered. The results This results into a lack of guidance on safe and efficient TBM operation and poor decisions on risk mitigation strategies. Due to limitations in current practice, the key questions are: how can we develop quantitative assessments? What sort of quantitative assessments are useful for tunneling applications? Here, we start with the ground investigations that are already done on a tunnel project. In the figure, you can see multiple vertical lines called boreholes with karstic voids within them that are drilled along the tunnel alignment. The boreholes involve drilling and extraction of the soil or rock samples from the ground. As a part of the proposed research solution, the three-step approach involves modeling of the ground using statistical methods and characterizing the void occurrence. Finally, the quantitative interpretations that include a probability of occurrence and the knowledge of the number and the size of the voids occurring within tunnel envelope are made. As an example, X voids of size V are expected with a probability between A% and B% in certain section of the tunnel alignment. This information will help all the tunnel engineers and involved stakeholders on the project to decide on appropriate risk mitigation strategies. A key aspect of the proposed research solution is the use of confidence levels on the interpreted results. For example, with 50% confidence, we can say that the cumulative void fraction, that is, the volume of voids in the ground, lies between 7% and 9% for the complete tunnel project. Confidence levels convey the uncertainty in the results. In this sense, the methodology is also characterizing the uncertainty in the interpreted results, and the quantitative assessments. Tunnel engineers can decide the level of uncertainty to live with. For tunneling projects, any improvement in the ground awareness is a significant value addition for the planning, design, and construction of tunnels. The methodology involves developing a 3D model of geological geotechnical conditions and karstic voids using geostatistical modeling techniques. Geostatistics is used to estimate the geological geotechnical conditions at unsampled locations using the data from the sample locations. That is, using the borehole data to interpolate between the boreholes. Hundreds of equally possible ground scenarios, as you can see on the top right, are constructed to quantify the probability of finding a specific void and the number of voids at any given location. Eventually, this is what we want to achieve prior to tunnel construction: an improved knowledge of void occurrence so that we can have safe, efficient construction without any undesirable events. In your bottom right, you can see the probability of voids being painted along the tunnel alignment before the TBM actually starts the excavation. In this study, the voids were considered to be spherical and were categorized on the median size from investigations. Tunnel engineers are often interested in voids of different sizes, as selective strategies to treat these voids can be adapted. Application of the methodology results into part 1 of quantitative assessment that gives the occurrence probability of each void category within the tunnel excavation envelope. Every division on the x-axis is about 100 meters of tunneling. That is about 20,000 cubic meters of excavation for an 8-meter diameter tunnel. As you can observe, relatively high occurrence probability of category V1 voids was observed in the first 50 to 100 meters of tunneling. Relatively high category V3 occurrence probabilities were found in the intermediate tunnel sections, and the same applies to category V2 voids, which were found in the intermediate tunnel section from about 900 chainage to about 1500 chainage. Darker colors indicate higher confidence levels, saying we are 95% confidence versus saying we are 25% confident. Wider the confidence level band, the higher is the uncertainty in the probabilistic estimates. The part 1 of the quantitative assessment gives an indication to a tunnel engineer on where can we expect voids and with what probability. Part 2 of quantitative assessment gives the number of voids within the tunnel envelope. As you can see, the black line indicates the average voids that were estimated from modeling, and the band gives the 95% confidence interval on the number of voids that are estimated. The number of voids for every 50 to 100 meters of excavation are added to get a cumulative count of the void category expected within the tunnel envelope. Results show that total of V1 voids expected is about 2 times that of the V2 voids. Now, the tunnel engineers are aware about what is the most category of voids to be encountered within the tunnel envelope and can plan accordingly prior to the tunnel construction. An important aspect of this quantitative assessment is the application in project bidding and project procurement. The results from geostatistical modeling are applied towards estimating the void fraction within the tunnel envelope for every 50 meters or 10,000 cubic meter of excavation. In this study, the average void fraction remains between 2% and 6%. However, Probabilistic results indicate it can be as high as about 12% in the intermediate tunnel section. Also, grouting, where a mixture of cement, admixtures, and water are injected into the ground to improve the ground conditions and fill the voids, is estimated in terms of confidence intervals in the plot on the bottom right. This provides an informed guidance on managing the risk and optimizing the TBM performance in karstic geological environments. Higher the void fraction, higher will be the estimated grouting quantities, and it is reflected in these figures. The probabilistic assessment can serve as a robust tool in estimating critical subsurface features and for project planning, design, and construction. With this, I would like to thank you for watching my presentation.